Many of us are interested in this idea of taking an AI like ChatGPT, which clearly has some form of intelligence, or at least apparent intelligence that you can treat as if it's real intelligence, and taking that same AI but putting it into an embodied agent. So by that I mean an AI that can move around in its environment, sense its environment, and learn new skills. For instance, one step further, you could use an AI like GPT-4, but have a system like Iron Man's J.A.R.V.I.S, which has access to all of his data. It's able to see what he sees, able to talk to him, give him alerts, and control his equipment. And you see the little holograms that he maneuvers around as he's designing the Iron Man suit. So this is basically like ChatGPT. You talk to it, it's conversational, but it doesn't have to wait for you to talk to it in order to respond. And also, obviously, it has way more capabilities in terms of how it can interact with the environment. Then beyond that, you get to something like Sunny from iRobot, Will Smith's sidekick, where it actually controls a body that's dedicated to it, and is able to have its own goals. In iRobot, they also have laws that the robots have to follow. This is because they're given a large amount of agency, and they're also, in some respect, given the ability to choose their own tasks and their own goals, as long as they conform to those overall laws. So as a step in this direction toward more agentic AI, Nvidia came out with this paper last year, which does use the intelligence from GPT-4, but uses it to control a bot in a Minecraft environment. So you might think it sounds simple. You just ask ChatGPT how to control the bot, it gives you an answer, and you use that data to control the bot. Unfortunately, it's not that simple. The main problem is that GPT-4 is very slow, or at least it's too slow to control an agentic AI in a real-time environment. It's fast in its own environment, which is generating internet text, but if you're then going to use a large chunk of that text to control something that needs quick reflexes, it's just not going to work. And I'm not just saying that GPT-4 is too slow on a random Tuesday when you have software developers across the US using it, asking it what's wrong with their Git push. GPT-4 is orders of magnitude too slow for the task at hand. So for instance, imagine you're a Minecraft bot, you hear a zombie noise behind you, or you sense that. Send off the data to ChatGPT, ask it what you should do next. It starts replying, "Oh, that sounds like it might be a mob looking to harm you." But before it even gets that sentence out, the mob is already attacking you. You're at the game over screen before you've gotten the full instructions from GPT-4. And this doesn't just apply to bots in a Minecraft environment. It applies to any agentic embodied AI operating in any real-time environment. Imagine it's a self-driving car instead of a Minecraft bot, and there's a motorcyclist coming down the center of the road, and it needs to take evasive action to make sure that it doesn't accidentally come into contact with the motorcyclist. It doesn't have time to ask ChatGPT what it should do and wait for the reply with 6 bullet points of how to deal with dangerous drivers. We need a way to leverage the intelligence of GPT-4, but we can't exactly wait for it in any sort of situation that requires real-time updates. So this was the problem that Nvidia was looking to solve in this paper. This idea of a slow, really smart intelligence, but then also the need for quick interaction with the environment. And the solution they came up with was pretty intriguing. I didn't realize it on my first reading of the paper, exactly how widely applicable this is. But they made the insight that while ChatGPT cannot respond super quick in a real-time environment, it can write code that can respond very quickly. So it can't immediately instruct the agent to turn around, pull out its sword, and start hacking away at the zombie. But it can write code to do all those things using the MindFlayer API, spawn in the bot, and have a library of functions that are available to be used for safety, gathering resources, etc. So this is a graphic from the Nvidia paper. You can see on the right is the skill library. It has things like mine wood log, craft stone sword, craft shield, and these are different skills that the Minecraft bot is going to learn. And the skill library is actually what's most interesting to me here, because that is the code base that it's creating. That's a library of functions that the bot can use. So the next question is, how does it choose which skills to create and add to the library next? And the answer is the automatic curriculum. So since GPT-4 understands what Minecraft is, it understands what bots are and what it means to learn new skills, you can basically ask GPT-4 to give you a curriculum for teaching the bot new skills. For instance, things like crafting stone weapons need to come before crafting iron weapons, because you need a stone pickaxe in order to mine the iron that's needed for the iron weapons. And since GPT-4 has read the internet, it knows about all these things ahead of time. So that is a key piece, that GPT-4 has to know about the environment that you're looking to put an embodied agent into. But it does know these things, so it can create the curriculum, and that generates tasks. And then basically you have this iterative prompting mechanism where it writes code for a new skill to complete the next task in the queue. And then you run the code, see if there's any syntax errors. If there are, it immediately fixes the code and goes again. And then at the end, once the code executes successfully in the environment, the bot actually performs the action, or at least gets through the full skill and tries to perform the action that it's supposed to perform. Then the self-verification mechanism, which is also GPT-4, it's just sort of another instance of GPT-4, then looks at the environment data and compares it with the definition of the task and determines whether the task was actually completed by this code or not. If it was completed, then that's when the code gets put into the skill library. If you're thinking about this in terms of general software development, it's kind of like how you write a piece of code, write a function. It's supposed to be a feature for, a new customer, and you want to make sure it's tested fully before it goes into the production code. So you write unit tests, write integration tests, do physical testing, that type of thing, before you put it into your code base. So same type of thing, that's the purpose of the self-verification module. One more thing I want to point out here is that these skills do actually build upon one another. So you can see the combat zombie function here builds on the craft stone sword and craft shield function. Those are skills that you have to develop ahead of time, and then those are incorporated into the combat zombie skill. So this is what makes it into more of a code base. The fact that you can have functions calling other functions, you have composition, not just a collection of isolated functions. So ChatGPT is able to create these skill functions, but then another issue arises when you think about how are you going to save these functions, and how is GPT-4 going to access these functions later in order to build upon them for new skills. So this is a graphic from the paper that shows the process that they came up with for this. Pretty smart. They use GPT 3.5. They feed it the code for the skill. It generates a description in text. You can see it says, the function is about equipping a stone sword to combat a zombie, etc., etc. So it takes that text that was generated with 3.5, probably to save costs, since 3.5 is a lot cheaper than 4.0. This is not a very complicated task. Takes the task and generates what we call a vector embedding. So vector embeddings are an interesting concept that's fundamental for large language models and GPTs. Basically, you can think of it as like a mathematical way to represent semantics in text. So you can take text and then you can convert it to a mathematical representation, just an array of numbers. And then that in some way represents what the text actually means. So the classic example I remember learning is you could take the embedding for king, the word king, subtract the embedding for man, add the embedding for woman, and you would get something approximating the embedding for queen. So that would give you a transformation from king to queen, and basically there's an intermediate step there where you take away man from king, and you're going to have an embedding that semantically approximates something like the concept of regality. So you generate this embedding, then you're going to store it in a database, and this is called a vector database because its keys are vector embeddings, and the values stored in the database are going to be the skill functions that you've created. So then that way in the future, you have a new task. Here they give the example of craft iron pickaxe. You want to generate a skill for crafting the iron pickaxe. You want to write the code for that. And so you're going to convert the task craft iron pickaxe into a text description in the same way that you did for the code above. And then you're going to generate an embedding from that and query the skill library. And then you're going to get the top 5 relevant skills to crafting an iron pickaxe. Remember, the embeddings embed information about the semantics of the text that you're embedding. So you're only going to get the things that are similar to your task at hand. You're not, for example, going to get the code for combating a zombie when you're trying to craft an iron pickaxe, because that's not really something that's going to help you craft the iron pickaxe. It's not related semantically. So this process of using vector embeddings to store information that then gets fed to GPT in the prompt is called retrieval augmented generation, or RAG. Not really a new concept. Maybe it was new at the time of this paper, but it's become pretty standard as a prompting practice nowadays. So you'll notice that all of these ideas in isolation are not groundbreaking at this point. You have GPT-4 generating snippets of code or single functions of code, which we all know it can do. You have creating vector embeddings and storing them in a database for retrieval augmented generation, which at this point is a fairly well-known practice. And then you have this idea of curriculum learning. You have GPT-4 generating a sequence of steps that the model has to perform in order to build skills on top of one another. And so you combine all these things together and you get something that actually works. You get a bot that's actually able to learn over time. And yes, it's all in code. It's not like you're training a neural network that's learning to do all these things, but still you're creating a system that has the type of intelligence that we're looking for. So you can see here a comparison of this Voyager method to a Voyager method without the skill library, and then also some other papers. So there's AutoGPT, which is an open source project for more agentic AI. You have the React paper, which is just sort of a prompting mechanism telling the model to think first and then act and then reflect on its actions and do that in a loop. That's something that has been proven to make GPT-4 better able to problem solve. But as you can see, the React method is barely able to make any progress in this task. You can see it's like collecting a couple different types of dirt, basically. AutoGPT is a little bit better. You can see it has more agency. It's able to craft some of these tools in order. But then you look at the two Voyager lines, the orange and the blue, and those are really on a new level. And the orange with the skill library is the best of all, and that's the only one that's able to generate a diamond tool within the time range that they've allotted here, which is a certain number of learning iterations. So why does all of this matter? Obviously, creating a bot to play Minecraft is not the most important task in the world. It might be a super fun way to play a game, but really what we're interested in is how do we build robots with this capability? I think a lot of people mistakenly think that the AI isn't really there yet, that GPT-4, while it shows apparent intelligence, can't really control robots. It can't do the motor function that's required. But I think this paper, first of all, shows because GPT-4 can write code, it can essentially perform motor control at the speed of light. There's no reason to think that we need to build an AI that's able to do both the slow, intelligent thinking and the fast motor reflex thinking. Consider humans as an example. We have a conscious thought process, which is analogous to GPT-4, And then we have our whole nervous system, which has reflexes that are sort of built in, and we don't have to think about these things. So there's quick reflexes, like our autonomic nervous response. And then there's also things like habits and skills, which are equally not conscious, I would say. Maybe there's a bit of more of a role of consciousness in it, but think about swinging a bat and hitting a ball. It's not really a conscious thing, hitting the ball. You're consciously doing the activity, but everything about actually hitting the ball is more ingrained, and that's why you need to practice a lot so that it becomes automatic. And in addition to this idea of code for reflexes and GPT-4 for consciousness, the Nvidia paper also gives us a blueprint for potentially how we can generate more advanced code bases using GPT-4. So yes, if you ask GPT-4 to write you some code, it's going to say it's only able to write a small piece at a time. It can only do little snippets, write little functions. But with the method that Nvidia has provided here, you can actually have those functions build on one another, and you can store the functions in a way that GPT-4 can easily retrieve them at a later time. And most importantly, Nvidia has demonstrated that the whole system works when you put it together. The code works, you're able to put together a code base that can actually control an agent in a real-time environment, and it's able to progressively learn more and more complex skills. It remains to be seen just how complex it can get, right? How much complexity can it handle? Is it infinite, or is there going to be a bound where suddenly GPT-4 is not really able to handle everything? So as a first step, I'm interested in reproducing the results of this paper. In terms of the OpenAI API usage, it might be a bit expensive, but I think there's ways around that. And then hopefully progress to more and more interesting ideas. I think if you could create a bot that doesn't just follow a curriculum to learn sort of random skills, but actually has an objective to survive in the environment, prevent death, maybe you incorporate some sort of evolutionary algorithm. I think there are a lot of potential interesting next steps. So that's about all I wanted to say for the Voyager paper. If you're interested in the implementation and the next steps, go ahead and subscribe, and I'll see you later.